This video, I'm going to take you through where trigonometry comes from. So trig is all about triangles, specifically right triangles, where one of the angles is 90 degrees, and this helps us figure out missing sides or angles, especially when we only are given a limited amount of information. So to begin with, we've got Joey here, and it's about the perspective of where Joey is standing. Notice he's in different spots. So if Joey is standing on angle A, then we would call this the opposite side from him. This would be the adjacent side, and this would be the hypotenuse. Now, how do we know which one's which? The hypotenuse is always across from the 90-degree angle. The opposite is always just directly opposite of where Joey is, and that leaves the adjacent to be the third one. So now in triangle number 2, Joey moves to angle B, so there's the opposite. Hypotenuse is always going to be in the same place. This time the opposite and adjacent just switch. Now if Joey is standing at angle C, the opposite and the hypotenuse are the same, which means we're left to try to choose which sides are the adjacent. And I put the question mark because we actually don't know which one is the adjacent. They can't both be adjacent. So you get kind of a weird case here in triangle 3. So now if we go back to our similar triangles, these two triangles I've given you have the same angles and their sides are different, but they are proportional to each other. So if we compare some things about these triangles, they should be true. For example, if I compare 10.42 divided by 14.77, that should be equal to the ratio of 13.6 to 19.28, because those are both the hypotenuse, and it also should be equal to 8.74 over 12.39. So we could show those ratios are, in fact, all equal to, if I get out my calculator, just show that they're all the same ratio to start with, to kind of convince you that these are similar triangles. Okay, so that's equal to this ratio. Let's just try the next one, 13.6 over 19.28. Okay, same ratio, and the 8.74. I just made these triangles in GeoGebra, so that's why they're kind of weird side lengths. And I've rounded them just to 2 decimal places. Okay, so we see these are all the same ratio. We have to start there because it's going to all depend on the fact that these are similar triangles, what we're trying to find here. We're going to do some other things with ratios, but just compare different ones, going back to this idea of opposite, hypotenuse, and adjacent. So if we compare the opposite divided by the hypotenuse on each triangle, that would give us this ratio in the small triangle. Opposite would be this one because he's directly across from Joey, and hypotenuse is 13.6 because it's directly across from the 90-degree angle, so that leaves this to be adjacent. Now, if we do the same thing in the large triangle, notice opposite, hypotenuse, we get the exact same decimal, the exact same ratio. Okay, and if we compare a different ratio, like adjacent over hypotenuse, so 10.42 over 13.6, and we do that for both triangles, we get a different number than the first one. That's because it's a different ratio, different comparison, but they're the same within the small and the big triangle. And then we can do another one. There's one more ratio, opposite over adjacent, which gives us, again, the same ratio for both triangles. Now, this isn't a coincidence. These are called the trigonometric ratios. And as long as you have similar triangles, these ratios will be consistent. They are built into your calculator, and we just have different names for them. So opposite over hypotenuse is the sine. Adjacent over hypotenuse is called the cosine. Opposite over adjacent is called tangent. Maybe you've heard of these, maybe not. Okay, now this question popped up. Would these still hold if we were standing on the 50-degree angle? So now Joey's going to switch and go over here in both triangles and just show that we're going to get the same thing. Okay, same triangles. Joey's just switched perspective. We do the opposite over hypotenuse, which is the sine of the angle. So I'd say sine of 50 degrees is 0.766. Okay, and I can show you on my calculator now. Now, it's not just for these two special triangles. If I say sine of 50 degrees, I get that same 0.766. It's just a few more decimals on the rest. Now, if we do the large triangle, of course we get the same thing because it's just the sine of 50. Now, if we do adjacent, that's cosine of 50. That's going to give us this ratio for both triangles. Now I can check my calculator. Cosine is cos 50. I get the same thing, 0.6426. It's just been rounded a little bit differently. So the calculator is obviously more accurate. It holds more decimals. And then opposite over adjacent is tan of 50. And we compare the same opposite over adjacent on each triangle, and we get this new 1.192. So check my calculator. Tan of 50 should be about 1.192, and it is. Okay, so now formally, instead of calling these by those names, like I said, we have sine, cosine, tangent. And one way to remember these is this acronym, SOHCAHTOA. SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, so then going back to the calculator, we can just kind of show this over again. Sine of 36.9 would be opposite over hypotenuse, so that'd be 3/5. Okay, which is exactly 0.6. Cosine would be adjacent over hypotenuse, so that would be 4/5, which is exactly 0.8. And then the tangent would be opposite over adjacent, which is 0.75. Okay, and then I can switch the ratios around. If I stand over here at angle G, now opposite over hypotenuse, the adjacent switches to the opposite switches to the adjacent because I switched angles. So now opposite over hypotenuse is 4/5, which is the same thing we got here. And the cosine is going to switch now to the 3/5, which is the same thing we got here. But the tangent, however, is going to completely flip around to be 4/3. Okay, so just going through these on the calculator, we can see again. Let's do sine of 36.9 and see it's almost exactly 0.6. And then cosine 36.9, almost 0.8, and tangent. And the reason why these are off by a little bit is because I rounded the angle. This angle is actually pretty close to 37. Let's see what happens if I just do 37. It's about the same. So actually the angle has been rounded. There's more decimals after the 9, so it's not quite 37. It's going too far. Okay, the other thing I wanted to show is where these angles came from, and then that'll be the last thing. So if I didn't know these angles, okay, let's go back. Pretend I don't know what these angles are, but I know the sides, 3, 4, 5. Then I can find these angles using my calculator. If I do, notice there's this sine with the -1 on top. So if I plug in the ratio of the sine, which was, I erased it now, which was the 3/5. If I plug in that ratio, it's going to give me that angle, 36.9. So yeah, there was 869 and so on. That's why. If I do sine of that answer, I should get exactly 0.6 now, which is 3/5. So then if I do cosine inverse of cosine was 4/5, I should get the 36.9 again. And then if I do tangent inverse, tangent was 3 over 4. I'm going to get that same angle. So we use these inverse functions with the -1 to figure out the angles. Okay, that's about it for this video. Thanks for watching. Hope that helps.